In the previous video, I introduced to you a coin example where we asked about the probabilities of various outcomes of tossing that coin. And then I introduced the very basic formalism for writing statements about the probability of various sentences in a formal language. In this video, what I will do is introduce some basic rules or concepts for how to calculate probabilities. And then after doing so, we will return to the coin example from the beginning and apply those rules to work through in more detail how to calculate the probability of the various outcomes we might be interested in. So the most essential and basic rule of probabilities is that probabilities are always between 0 and 1. So we often talk about probabilities in terms of percentages or odds, and this may be confusing, but let me explain that for you. When you say there's a 20% chance of snow tomorrow, that means that the probability of S, so here we're assuming S stands for that it will snow tomorrow. When you say the probability of that snow tomorrow is 20%, you can write that as saying that the probability, or PR, of S equals 20 over 100, which is the same as writing 1 over 5, which is also the same as writing 0.2. So any of these numbers, 20%, 20 over 100, 1 over 5, 0.2, these are all equally valid ways of expressing the same claim about the probability of S. So that is how, given that probabilities are between 0 and 1, that's why we can talk about them being percentages. In terms of odds, when you say the odds, for instance, of heads versus tails on a coin flip are 50-50, what that means is that the probability of H, so in this case H means that the coin will land heads, the probability of H equals the probability of T, which means that the coin will land tails. Their probabilities equal 50 over 100, which is the same as 1/2, so you're just simplifying the fraction as you do here, which is also the same as a decimal 0.5. And we could also say that the probability of H and the probability of T are both 50%. So this is how we connect talk of percentages and odds with the idea that probabilities are always between 0 and 1. So a probability can be 0, as we'll see, and it can be 1, as we'll see, and it can also be any fraction in between, or even any real number in between 0 and 1. However, for simplicity in this class, we'll be, for the most part, sticking to pretty simple values between 0 and 1. So the next and very important rule is that if a sentence phi is a logical truth, then the probability it is assigned is 1. So the reason, again, that I'm using a fancy Greek letter here is that phi is not going to be just a simple sentence like A or B or C, because simple sentences like that are never logical truths. So phi has to be a complex sentence built up out of simple sentence letters with connectives, and we'll see an example in a second. So that is to say, though, that logical truths are always very complex sentences. And what this rule says is that any sentence which is a logical truth has to be assigned a 1 probability. That is to say that any logical truth is wholly certain. So hopefully that should be intuitively clear why that is a good rule. Now the flip side of that is that if a sentence phi is a logical falsity, that is, if it's a contradiction, then its probability is 0. So to repeat, any logical truth or tautology has 100% probability, and any logical falsity or contradiction has 0% probability. So here is an example. So suppose that H means that some coin will land heads, and T means that it will land tails, which is, hopefully you can see that it's the same. If a coin lands tails, that is the same as it not landing heads. And I'll return to this in 1 second, because this is an important point when we think about the tools of deductive logic when we're applying these rules of probability. But intuitively, when we're talking about a single coin toss, the probability that it will either land heads or tails is 1. So it's certain that when we toss this coin, it will land either heads or tails. It'll land on one of its sides. And the flip side is that the probability that it will land on both heads and tails is 0. So there's a 0 probability that it will land on both of its sides. Now, the reason for that is that we are considering the sentence H or T as a logical truth. And then, therefore, by this rule here, it must be assigned probability 1. And we're similarly considering H and T as a logical falsity. And therefore, by the second rule, it must be assigned 0. But now let me return to this qualification here. So if you were to make a truth table for the sentence H or T, you would notice that actually it's not a logical truth or a tautology. You would notice that if you were to simply create a truth table where you had H and T as the atomic sentence letters, you would notice that it's possible to assign H and T both false, which is to say that it's possible for this sentence H or T to be false, which is to say that it is not a tautology. But here, and this is very crucial that you understand this moving forward with the formalism in probability theory, when we're talking about coin tosses, say, and using letters like H and T, we're assuming that in the background that T holds just in case not H holds. So that is to say that we're assuming that if the coin lands tails, then it doesn't land heads, and also if the coin doesn't land heads, then it lands tails. Or a more simple way of putting this point is that what we're doing is we're writing H and T instead of, say, H and not H. So instead of writing T to stand for the possibility that the coin lands tails, you could just write not H to represent that possibility. And so what we would have here then is that we'd be asking about the probability of H or not H. And H or not H is a tautology, so therefore it must be assigned 1. And in this case, we'd be asking about the probability of H and not H. And that is a logical falsity, as we saw in the previous unit, and so therefore must be assigned 0. So what you have to note moving forward is that here, and in similar cases, which I'll emphasize in the future as well, but in this case, for instance, when we talk about H and T standing for the coin landing heads or the coin landing tails, implicitly we're assuming that T is basically the same as not H. Or that's to say that another way of putting that is that we're assuming that T if and only if not H. So that means that H or T in this case is a logical truth and therefore must be assigned 1 by this rule here. And similarly, H and T is a logical falsity, so thus must be assigned probability 0 by this rule here, the second rule. So those are the rules. So these two rules here tell us the probabilities of tautologies and contradictions. So in addition to knowing that all probabilities must be between 0 and 1, and then that a logical truth is at the top with probability 1, and any logical falsity is at the bottom with probability 0, we can also calculate the probabilities of disjunctions. And the way we do that is sometimes simply add the probabilities of the disjuncts. Now it's important to know that we can only do this sometimes, and I'll tell you exactly when in a moment. It depends whether the propositions being disjoined are mutually exclusive or not. So as I've stressed already, this idea of mutual exclusivity you'll see in probability theory just is the exact same notion as we saw last in the previous unit of inconsistency or joint unsatisfiability. So two propositions, phi and psi, are mutually exclusive just in case they are inconsistent. And what that means, if you can recall, what it means for phi and psi to be inconsistent is for it not to be possible for them to be true together. So in terms of truth tables, what that means is that on the joint truth table for phi and psi, there is no row on which they're both true. So again, what it means for two propositions to be mutually exclusive is for it not to be logically possible for them to be true together. And if two propositions are mutually exclusive, if it is impossible for the two propositions phi and psi to be true together, then we can calculate their disjunction by simply adding together their probabilities. So in the case where phi and psi are mutually exclusive or inconsistent, then the probability of phi or psi equals the probability of phi plus the probability of psi. So for instance, suppose that the probability of an ace, so in this case what we're doing is instead of tossing a coin, what we're doing is we're drawing cards randomly from a standard deck of cards. So the probability of drawing an ace is 1 over 13. The probability of drawing a face card, like a royalty, is 3 over 13. So that means that if the probability of drawing an ace is 1 over 13, and the probability of drawing a face card is 3 over 13, we can conclude by this rule here that the probability of drawing either a face card or an ace is 4 over 13. And that's because whether the card you draw is an ace and whether it's a face card are mutually exclusive. That is to say that there are no cards that are both aces and face cards. So to put this a bit more formally in terms of the actual calculation, here we have F standing for that you draw a face card, and A standing for that you draw an ace. So when we ask about the probability of drawing either a face card or an ace, we have that the probability, that we're asking about the probability of F or A. And now, since it's mutually exclusive, you drawing a face card or you drawing an ace, we can apply this rule here and conclude that the probability of F or A equals the probability of F plus the probability of A. And then from reflecting on the number of total cards in the deck, as well as the number of face cards versus and also the number of aces, we can just fill out what these individual probabilities are as we have here. So the probability of a face card is 3 over 13, and the probability of an ace is 1 over 13, and we just add those up to get that the probability of F or A is 4 over 13. So now note that just like I was talking about with mutually exclusive propositions about tosses of a coin, we're making similar assumptions. So that is to say that if you built a joint truth table for the atomic sentence letter the atomic sentence letter F and the atomic sentence letter A, you would find that they're actually not mutually exclusive. That is to say that if you simply had these two atomic sentences, it's possible to assign them both the truth value true. So it's important to note that in the application, in how we're applying this notion of mutual exclusivity here, we're actually assuming as a background assumption that a card is a face card just in case it's not an ace. That is to say that we're assuming that there are no face cards that are aces. So in these rules that you've seen now and some more you'll see to follow, what you can do is you can draw on your ability from the previous unit to test whether two sentences are, say, mutually exclusive, that is, inconsistent. Or you can draw on your ability to test whether a sentence is a logical truth. And in that case, you know that it has the probability 1, say. But in drawing on that ability, and when, for instance, constructing a truth table to verify these things, it's crucial that you understand in our current applications that we're making certain abbreviations. So here we're treating F and A as being mutually exclusive, even though if you were to, very strictly speaking, create a truth table with just F and A, they would not be, because we're abbreviating for this to understand that we're talking about a face card. With F and A, we understand we're talking about an ace, and we understand as a background assumption that there are no cards that are face cards and aces, and that's why F and A are mutually exclusive, and that's why, therefore, when we calculate the probability of their disjunction, we simply add up their individual probabilities. Okay, but as I've just stressed, you can only add up the individual probabilities in this simple way to calculate a disjunction. You can only do that when the two propositions are mutually exclusive, when the two disjuncts are mutually exclusive. So, to see how that is important to notice that, consider the following. Imagine you're rolling a regular 6-sided die. So the probability of rolling an even number is 1/2, because half the numbers on the die are even. The probability of rolling a 6 is 1/6, because only one of the numbers is a 6, and there's 6 possible outcomes. So we know the probability of rolling an even number is 1/2, and we know the probability of rolling a 6 is 1/6. But we cannot calculate the probability of rolling either a 6 or an even number by simply adding up 1/2 and 1/6. So if we add up 1/2 and 1/6, what we get is 4/6, or 2/3. Okay, but the probability of rolling either a 6 or an even number is not 2/3. And the reason for that is that 6 is an even number. So that is to say that rolling an even number is not mutually exclusive from rolling a 6. It's possible to do both. And specifically in the case where you do roll a 6, you also roll an even number. So in a future lecture, I think next week, I will give you a rule for calculating the probability of disjuncts when the disjuncts, sorry, let me repeat that. Next week, I will give you a rule for calculating the probability of a disjunction when the disjuncts are not mutually exclusive. But the rule that I'm giving you now can be applied in many cases as long as you're sure that the disjunction contains mutually exclusive disjuncts, and in that case you simply add them up. But it's very important that you do not apply this rule to disjunctions where the disjuncts are not mutually exclusive. So just as I've given you an initial rule for calculating the probability of some disjunctions, i.e. when you have mutually exclusive disjuncts, there's also a rule for calculating the probability of conjunctions. And just like the rule for calculating the probability of disjunctions is limited to certain cases, this rule also can only be applied in certain cases. So to determine the probability of a conjunction, you can sometimes, but only sometimes, simply multiply the probabilities of the conjuncts. And just like I will give you a fuller rule next week to calculate disjunctions where you do not have mutual exclusivity, in the next lecture in a couple of days, I will give you a rule for calculating conjunctions which do not satisfy this special condition. But for now, let me just give you this initial rule. Now, this rule I'm about to give you, i.e., the rule of simply multiplying the probabilities of the conjuncts of a conjunction, whether you can apply this rule depends on whether the conjoined propositions are independent or not. Now, the notion of independence already came up. Two propositions are independent just in case the truth of one does not influence the probability of the other. That is to say that one does not make the other more likely. They are independent. Now, I'll return to this in a few slides, but also in the next lecture, in a couple days, we will give a more precise definition of independence. So, the rule for multiplying probabilities is that if you have two propositions, phi and psi, which are independent, then the probability of phi and psi equals the probability of phi times the probability of psi. So when you know that the two conjuncts are independent of one another, then you can calculate the probability of their conjunction by simply multiplying their individual probabilities. So for instance, with a fair coin, the probability of getting heads on both the first and the second toss can be calculated as follows. So the probability of heads on toss 1 and heads on toss 2 equals, by this rule of multiplying probabilities, simply the probability of heads on the first toss times the probability of heads on the second toss. And we can apply this rule precisely because we have a fair coin, and part of what it means for the coin to be fair is that what happens on one toss does not influence what happens on another toss. Each time you toss this fair coin, it's an independent process. So that is to say that however it lands the first toss, if it lands heads, that does not have an effect on whether it will land heads for the second toss. So that is to say that whether you get heads on the first toss is independent of whether you get heads on the second. So therefore, the probability of heads on the first toss and heads on the second toss is simply the probability of heads on the first toss times the probability of heads on the second toss, which is their individual probabilities, because each of heads and tails is equally likely, so you have 1/2 chance of heads on the first toss and then 1/2 chance of heads on the second toss, and so 1/2 times 1/2 equals 1/4. Now, again, I will return in the next lecture to how you can calculate conjunctions without independent conjuncts. But it's very important to note that you cannot apply this rule here of simply multiplying probabilities if the conjuncts are not independent. So you cannot calculate the probability of getting both a heads and a tails on the first toss as the probability of heads on the first toss and tails on the first toss equals the probability of heads on the first toss times the probability of tails on the first toss, which is, because there's half a chance of each, you'll eventually get 1/4. But it's not true that the probability of getting both a heads and a tails on a single toss is 1/4. As we noted above, the probability of getting both a heads on the first toss and a heads on the second, as we noted above, the probability of getting a heads and a tails on a single toss is 0. And you can review why that is. Now, the final rule which I'll give to you here is that if propositions phi and psi are logically equivalent, then they have the same probability. So this is a very important rule because it's very common in working with probabilities that you must swap out the probability of a proposition with the probability of a logically equivalent one. So there's many cases in which you will be asked about the probability of a given proposition, but you only know from the question what the probability of some logically equivalent one to it is. So what you can do is, if you know the probability of the logically equivalent one, you know, therefore, the probability of the one you're being asked about. And you can use your tools from the previous unit to verify whether two propositions are logically equivalent or not. So you can create a joint truth table and ask whether the two propositions always have the same truth value under their main connective. So again, verifying whether two propositions are logically equivalent will rely on your knowledge of propositional logic, which we developed in the previous unit. And it's important to note that sometimes the logical equivalencies you must rely on are not obvious, so they're not intuitive, so you have to use your in-depth knowledge of propositional logic and testing for equivalence to establish them. So for instance, one non-obvious logical equivalence that's very important to keep in mind for probability theory is that any sentence A is equivalent to this very complex sentence, A and B, or A and not B. So these two sentences here, A and B, or A and not B, are logically equivalent. If you were to create a truth table for a joint truth table for them, you would see that they always have the same truth value. So these, therefore, by this rule, must have the same probability. All right, so here on this slide is a summary of the basic concepts or rules that I just introduced to you. And what I recommend you do is that you actually copy these down into a notebook for future reference, because these are very important in solving the various problems you'll be presented with. So the first is that for any sentence, it has a probability between 0 and 1 inclusively. The next is that any logical truth gets probability 1. There's then that any logical falsehood gets probability 0. We then have that when you have mutually exclusive propositions, their disjunction can be calculated by simply adding up the probabilities of the disjuncts. We then have that if you have independent propositions, their conjunction can be calculated, the probability of their conjunction can be calculated by multiplying the probability of the conjuncts. Then we have that if phi and psi are logically equivalent, then they have the same probability. And this final rule here, which is important to note at this point, but I'll return to it in a future lecture. I haven't introduced it above, but that is that for all phi, the probability of its negation, the probability of not phi, is 1 minus the probability of phi. So I have put a little asterisk beside some of these rules, and I think there should also be a little asterisk here. Now what that signals is something that we will not get into in detail in this class, but that signals that some of these rules are more foundational than others. Some of these rules are the axioms of probability, and based on these axioms, and we'll introduce some more axioms later, but based on all the axioms, we can then derive some of the less fundamental rules, for instance, the ones without asterisks here. But we will not get into the details of axiomatic probability theory in this course. What you just have to note is that all of these are legitimate rules that you can appeal to in calculating probabilities. Now, before I conclude this lecture by returning to the coin example from the very beginning, let me just say something about the notions of mutual exclusivity and independence, which are appealed to in these basic rules for calculating certain disjunctions and certain conjunctions. So it's crucial that you do not conflate exclusivity with independence. Exclusivity is a deductive concept. As I've stressed, what it means for two propositions to be mutually exclusive is for them to be inconsistent. So that is to say that on their joint truth table, there is no row on which they're both true. That is to say that it's logically impossible for both sentences to be true together. So whether or not two propositions are mutually exclusive is a matter of deductive logic. But independence is not a deductive concept. It's an inductive or probabilistic concept. what it means for two propositions to be independent is that the truth of one does not affect the probability of the other. They do not make each other more or less likely. They're probabilistically independent. Okay, so mutual exclusivity or inconsistency has to do with deductive logic, what is logically possible. But independence has to do with what's probable. Specifically has to do with whether two propositions do not affect each other's probability. So here are some examples to illustrate how these are different, how these two concepts are different. So when you have mutually exclusive propositions, those are usually not independent. So for a fair coin, it cannot land heads and tails on the same toss. So H and T are mutually exclusive. As I've stressed before, T is essentially just not H. So H and not H can never both be true. It's logically impossible for the coin to land heads and not heads at the same time. So H and T are mutually exclusive, but they're not independent. Because if the coin lands heads, then the probability that it lands tails changes from 1/2 to 0. So before you flip the coin, the probability that it's tails, that it will land tails, is 1/2. But if you then flip it and you learn that it's true that the coin lands heads, then the probability that it has landed tails drops to 0. So that is to say that the truth of the coin landing heads does influence the probability of it landing tails. It brings the probability down from 1/2 to 0. So here we have two propositions which are mutually exclusive, which cannot be true together. And precisely for that reason, because the two propositions are mutually exclusive, they are not independent. The truth of one makes the other one completely unlikely. Now here is an example of independent propositions that are not exclusive. And in general, whenever you have independent propositions, they are not exclusive. So whether I have pizza for lunch tomorrow, that proposition that I have pizza for lunch tomorrow is independent of whether Justin Trudeau has pizza for lunch tomorrow. Justin Trudeau is the Prime Minister where I am right now in Canada. So the proposition about him, whether he has pizza for lunch tomorrow, is independent of the proposition that I have pizza for lunch tomorrow. That is to say that whether I have pizza for lunch tomorrow has no bearing on the likelihood of whether he will, and whether he will has no bearing on the likelihood of whether I will. So these are two independent propositions. But these two propositions are not mutually exclusive. It is logically possible for both myself and Justin Trudeau to have pizza for lunch tomorrow. So these two propositions are independent, but they're not mutually exclusive. So the idea of mutual exclusivity is very different than the notion of independence. They come apart. So now that we have these tools under our belt, and these tools are rules for calculating the probabilities of given sentences, and a couple of the important ones tell us how we can calculate some disjunctions and some conjunctions, and they rely on the notions of mutual exclusivity and independence, which we have covered again here. Let's now return with all of this to the simple coin example from the beginning, where we flipped a fair coin twice in a row, or we were going to at least, and we are wondering about the probability of getting one heads and one tails, regardless of the order. So there are two ways to get one heads and one tails, HT and TH. So here I've formalized for simplicity. I'm following a certain convention, which I will follow moving forward, so it's important here to emphasize this notational convention. So here I've written HT side by side. Now that is an abbreviation for the full sentence of our logic, which is H1 and T2. So H1 and T2 says that there will be heads on the first toss and tails on the second toss. But here, what I do is I put H and T in a certain order. So because H comes first, that means I'm talking about heads into the first and tails, and then because tails is second, that signals that I'm saying tails come second. So HT stands for H1 and T2. And then TH stands for T1 and H2. So this is a notational abbreviation, which I'll use. So these are the two ways that you can get one heads and one tails. You can get heads first and tails second, or you can get tails first and heads second. So the event of getting one heads and one tails is compound, in the sense that there are two mutually exclusive ways for it to happen. So getting heads first and tails second is mutually exclusive from getting tails first and heads second, because there's different outcomes. So here we have identified the outcome of getting one heads and one tails with either one or the other, of two mutually exclusive particular ways of things turning out. So another way to put this is that we translate one heads and one tails as HT or TH. That is to say that when we're asking about the proposition that we get one heads and one tails regardless of the order, the way we formalize that is we're asking about the proposition HT or TH. And another way of putting this is that one heads, one tails is simply just equivalent to HT or TH. So whether you think of it as translation or equivalence, either way is fine. So now, given equivalence and mutual exclusivity, okay, so given that one heads and one tails is equivalent to this disjunction, and we know this is a disjunction between two mutually exclusive disjuncts, we can apply the rules. We can start applying the rules from above. So the probability of getting one heads and one tails is equal to the probability of HT or TH, because these are equivalent. And because HT, getting heads first and tails second, is mutually exclusive with tails first and heads second. Sorry, let me repeat that. Because getting heads first and tails second is mutually exclusive with getting tails first and heads second, we can calculate, given the rule above, or which I gave a few slides up, we can calculate the probability of this disjunction by simply summing or adding together the probability of each of the mutually exclusive disjuncts. So therefore we know that the probability of one heads and one tails will equal the probability of getting heads on the first flip and tails on the second, plus the probability of getting tails on the first flip and heads on the second. And now, here we're wondering about the probability of two conjunctions. And furthermore, because we know it's a fair coin, where the outcome of each toss is not influenced by the earlier ones, we know that we have conjunctions here of independent propositions. So H and T are independent. And so for that reason, we can apply the rule for calculating the probability of conjunctions with independent conjuncts. So here I've applied that rule. So the probability of HT plus the probability of TH is equal to the probability of H on the first time times the probability of tails on the second, plus the probability of tails on the first times the probability of heads on the second. So now here we have an equation where the numbers which we have to fill in are just simple probabilities of these simple sentences. And since we know it's a fair coin, we know that all of these are going to be 1/2, because we know that for each flip, it's a probability of 1/2 for heads and 1/2 for tails. So we simply fill in those numbers. So we replace each of these probabilities with 1/2, which we know from the fact that it's a fair coin. And the rest is just some simple math. So we get 1/4 plus 1/4 equals 1/2. And that is how these rules have told us that the probability of getting one heads and one tails is not 1/3, but is actually 1/2. Now, a slightly simpler calculation can give us what the probability of getting 2 heads is, as well as getting the probability of 2 tails. So I think I'll put this in the assignment questions for this week. So I'll leave that to you to answer these questions simply by applying the rule for conjunction that I've just given you.